Okay, let's start the stream. Magnetism and matter. Question solving. First question. When a bar magnet is placed at 90 degrees to a uniform magnetic field, it is acted upon by a torque which is maximum if the force acting on the magnet or torque acting on the magnet if the torque should be half its original value, then what should be the angle of inclination? Solution. They're asking theta value at what angle tau will be half of its original value. We know tau, which is equals to mb sine theta, and it can only be maximum when theta equals 90 degree, where this will become 1 tau max, which is equals to mb if it should be half of its value, t max by 2, which is equals to mb sine theta, then tau max, which we know it's mb by 2, which is equals to mb sine theta, which is equals to 1 by 2. So theta value therefore which is equals to 30 degree. The magnet should be inclined in such a way that it will make an angle of 30 degrees. Now let's go to the next question. A bar magnet of magnetic momentum m1 is suspended by a wire in a magnetic field the upper end of the wire is rotated through 180 degrees then the magnet rotated through 45 degrees. Under similar conditions, another magnet of magnetic momentum of M2 is rotated through 30 degrees. Then ratio of magnetic momentums, that is M1 by M2, is, okay, they're saying a bar magnet of magnetic moment M1. It is suspended by a wire in a magnetic field. There is a wire that is holding a bar magnet in a magnetic field. If the upper end of the wire is rotated through 180 degrees, then the magnet is rotated through 45 degrees. And there is another magnet which is in similar conditions, same wire holding this one as well. It is also rotated by 180 degrees. But the magnet was rotated by 30 degrees only. Then find M1 by M2. There is a formula. Solution: C alpha minus theta is equals mb sine theta. This is the rotation of the upper wire, where for first magnet C 180 minus 45 is equals to M1 B sine 45 degree, which is 1 by root 2. For second magnet, C 180 minus 30 degree, which is equals to M2B sine 30 degree, which is 1 by 2. By dividing both of the equations, we will get C cancel, B cancel, and we will get 135 by 150 is equals to M1 by M2 times 2 by root 2, which we can rationalize. We'll get it as, this one we can divide by 15, 10s are 9s are 9 by 15, which is equals to M1 by M2 times 2 root 2 by 2. Wait a second, this is 10, not 15. 9 by 10, 9 by 10 root 2, which is equals to M1 by M2. Now let's go to the next question. A magnetic dipole is under the influence of two magnetic field. The angle between the field directions, the two field directions, the 2B is 60 degree, and one field B1 is B1 equals 1.2 into 10 power minus 2 Tesla if the dipole, which is in under these two fields, comes to an equilibrium at an angle of 50 degrees with this field, what is the magnitude of the other field? Now let's solve the question. Since we know that the magnet is in the dipole is in equilibrium, we know torque due to each field should be equal and opposite. So mb1, which is equal mb1 sine theta 1, which is equals to mb2 sine theta 2, cancel, and theta 2, which is inclination with respect to b2, which is equals to 60-degree total inclination, total difference, which they have provided in the question, minus 15-degree, the first one, is equals to 45-degree. So b2, which is equals to b1 sine theta 1 by b2 sine b1 by sine theta 1 by sine theta 2, which is equals to b2. Substituting values, we will get b2, which is equals to 1.2 into 10 power minus 2 into sine 15 degree by sine of 45 degree. Now the value of sine 15 degrees has been provided in question, which I didn't write in the question, but I will write now. Minus 2 sine 15 degree value, they gave it as 0.2588, and sine 45 degrees is 1 by root 2, so it will come up root 2. B2 magnitude is finally approximately equal to 4.39 into 10 power minus 3 Tesla. Now let's go to the next question. A magnet is suspended at an angle 60 degrees in an external magnetic field of 5 into 10 power minus 4 Tesla. What is the work done by magnetic field to bring it in its direction. And magnetic moment of the magnet, which is given as 20 ampere meter square. Now solution, work done, which is equals to mb times cos theta 1 minus cos theta 2, where work done, which is equals to 20 into 5 into 10 power minus 4 cos theta 1, which is 60 initial angle, cos 60 minus cos 0 degree. So work done, which is equals to 100 into 10 power minus 4 minus 1 by 2. So work done is basically equal to minus 5 into 10 power minus 3 joule. Now let's go to the next question. A magnetic field, a magnetic needle lying parallel to a magnetic field requires W units of work done to turn it through 60 degrees. Then what is the torque needed to maintain the needle in that position? Solution, work done, which is equals to mb cos theta 1 minus cos theta 2, tau, which is equals to mb sin theta, theta 1, which is equals to 0 degree, and theta 2, which is equals to 60 degree. These are the main formulas. They are saying a magnetic needle is lying parallel to a magnetic field. Both the magnetic needle and magnetic field are in the same direction, angle between them 0 degree. If work done to turn it through 60 degrees, we turn it through 60 degrees the work done in doing that is 60 degrees. I mean W units or W joules. Then what is the torque needed to maintain the needle in that position? Now cos initial is 1 and cos theta 2, which is 60 degrees. So work done should be equal to mb by 2, 1 minus half, so 1 by 2, and torque, which is equals to mb sine 60 degrees. Sine 60 degrees equals root 3 by 2. So from this equation here, we can get the value of mb, which is equals to 2 work done. Now substituting this value in this equation, the main torque equation, we will get that torque, which is equals to 2 work done root 3 by 2, which is equals to work done, which is equals to W root 3. If we had values, we could have substituted, but since we didn't get values and it was only provided that the work done was W units, we substituted it. Now let's go to the next question. A bar magnet has a magnetic moment 2.5 joule per Tesla, and it is placed in a magnetic field of 0.2 Tesla. Calculate the work done in turning the magnet from parallel to anti-parallel position relative to field direction. They're asking if there is a magnet in the plane of in the direction of magnetic field. If we want to turn it to the direction anti-parallel, which is theta equals 180 degree, what is the work done? Formula for work done, which is equals to mb cos theta 1 minus cos theta 2, theta initial, which is equals to 0, theta final, or theta 2, which is equals to 180 degree. W, which is equals to magnetic moment, they gave it as 2.5. Magnetic field, they gave it as 0.2, and cos theta 1, 1 minus of cos 180 degree is minus 1. So minus of minus 1. So work done is equals to 2 times 2.5 times 0.2. So work done which is equals to 1 joule. Direct formula substitution. A bar magnet with poles 25 centimeter apart, dipole length, and pole strength 14.4 ampere meter, rests with its center on a frictionless pivot. It is held in equilibrium at 60 degrees to a uniform magnetic induction or magnetic field 0.25 Tesla by applying a force F at right angle to its axis 10 centimeter from its pivot. Calculate F and what will happen if F is removed. They're saying that a bar magnet with poles 25 centimeter apart and pole strength 14.4 ampere meter rests with its center on a frictionless pivot. Okay, there's a 25 centimeter long magnet and it has a pole strength of 14.4 ampere meter. It is resting on a pivot, something like this. This is a pivotal point, a frictionless pivot. It is held in equilibrium at 60 degrees to uniform magnetic field 0.25 Tesla by applying a force at right angle to its axis. It is like this. The magnet, if we assume this is magnetic field, the angle between them is 60 degrees and there is a force acting like this. So here we can say torque, that is mb sine theta or sine 60 degree, which is equals to force times or perpendicular distance or basically fr sine theta. Here this theta is theta 1 and theta 2. This theta 1, which is equal to 60 degree angle between magnetic field and magnetic moment. This theta, since they gave it is perpendicular, theta 2, which is equals to 90 degrees. So mb root 3 by 2, which is equals to fr times 1, and mb we can write it as pole strength times r. So we can substitute r value, which they gave as 25 centimeter. 25 into 10 power minus 2 times the pole strength, that is 14.4 times root 3, which is 1.7 by 2, 25 into 10 power minus 2. We'll get it as 7.2. Or is the perpendicular distance different? And there is value of Tesla, that is 0.25, that is magnetic field. But I believe we should not take this as 25 into 10 power minus 2. The r value should be 10 into 10 power minus 2. The perpendicular distance is 10 into 10 power minus 2 into 2. 1s are 7.2s are, and finally substituting we will get F equals 7.8 Newton approx. When F is removed, when this force, they asked what will happen if F is removed. If this force F is removed, the torque M cross B, that is torque, will be, it will go to an unbalanced condition, and the magnetic will, and the dipole or magnet will start rotating, and it will align itself so that the angle between them is 0 degree. Okay, next question. Now next question is, example, two bar magnets when placed one over the other there is, I believe, no time period of suspended magnet in the uniform magnetic field in the current syllabus of NEET. The question is about two bar magnets when placed one over the other. Takes 3 seconds for one vibration in uniform magnetic combination or magnetic field. If one magnet is reversed, the combination takes 4 seconds for one vibration. Find the ratio of their magnetic moments. I don't think this kind of questions are there. Okay, let's go to the next question. Now the next question is, magnetic field of 1600 ampere per meter produces a magnetic flux. Just a minute. Okay, then 1600 ampere per meter produces a magnetic flux of 2.4 into 10 power minus 5 Weber in a bar of iron of cross section 0.2 centimeter square. Calculate permeability, that is mu m, and susceptibility of the bar. Susceptibility is chi. If there is a magnetic field of 1600 ampere per meter and it is producing a magnetic flux of 2.4 into 10 power minus 5 Weber in a bar of iron of cross section 0.2 centimeter square, then calculate permeability and susceptibility of the bar. Now solution, we know that B, which is equals to phi by A. Magnetic induction, which is equals to phi by A. Okay, this is not a magnetic field, this is a magnetizing field. Magnetizing field is basically the H value, magnetic intensity of the magnetic field, that is 1600. So based on this we can find magnetic field or magnetic induction value, where magnetic flux was 2.4 into 10 power minus 5, area was 0.2 into 10 power minus 2 whole square, wait, not whole square, power minus 4 minus 4. Now we can take it as 1s are 12s are, B, which is equals to 1.2 into 10 power 0, so 1.2 Weber per meter square, or basically Tesla. Now if you want to calculate permeability, that is mu m, which is equals to B by H, and which is 1.2 by 1600, which we will get as 7.5 into 10 power minus 4 Henry per meter. And second, susceptibility, mu, which is equals to mu naught times mu r, is equals to mu naught times 1 plus chi. So mu value which we found was 7.5, or mu m value 7.5 into 10 power minus 4, which is by 4 pi into 10 power minus 7 plus minus 1, which is equals to chi value. We will get chi, which is approximately equal to 596.1. There is no unit for susceptibility. Now let's go to the next question. The permeability that is chi, no, not chi, of a substance is 6.28 into 10 power minus 4 Weber per ampere meter. Find relative permeability and susceptibility. We know that the permeability of a substance, the relative permeability, and chi are all dependent on each other. If one we know, other we can find. And we know the formula mu, which is equals to mu naught, I mean mu naught times mu r. So mu r, which is equals to mu by mu naught, which is equals to 6.28 into 10 power minus 4 by 4 into 3.14 to 10 power minus 7, that is 1s are 2s are 1s are 2s are, which is equals to mu r, which is equals to 0.5 into 10 power 3, or basically 500. Mu r, which is equals to 500. Mu r, which is relative permeability, is unitless. Now mu r, which is equals to 1 plus chi, so 500 minus 1, which is equals to chi, which is equals to 499. It's a very strong susceptible substance, whatever the substance is. Now let's go to the next question. The magnetic moment of a magnet of mass 75 gram is 9 into 10 power minus 7 ampere meter square if density of the material of magnet is 7.5 into 10 power 3 kg per meter cube, then find intensity of magnetization. Intensity of magnetization. Solution, they gave that it's a magnetic moment of 9 to 10 power minus 7 and density of the material is 7.5. So they're asking intensity of magnetization. Intensity of magnetization is nothing but individual magnetic moment or magnetization or like total magnetic moment per unit volume. And since we know that we know the mass of the substance, we need to find, we do not, and we also know the magnetic moment of the material. So what we need to find is volume of the material. They gave a relation rho, which is equals to density, which is equals to mass by volume. So volume, which is equals to mass by rho. So volume, which is equals to mass, 75 grams, 10 power minus 3. Density, they gave it as 7.5 into 10 power 3. Ones are tens are. So volume is basically 10 power minus 5. Yes, 10 power minus 5 meter cube. 10 power minus 5 meter cube. I is equals to magnetic moment by volume is equals to 9 into 10 power minus 7, that is magnetic moment, by 10 power minus 5 is equals to 9 into 10 power minus 2 ampere per meter. This is not current. This is intensity of magnetization, which is equals to 9 into 10 power minus 2 ampere per meter. Next question. A magnetic field strength, meaning H value, not the B value, which is 3 into 10 power 3 ampere per meter, produces a B magnetic field of magnetic induction of 12 pi Tesla in an iron rod. Find relative permeability of the iron rod. Solution: mu, which is equals to B by H, where H mu, which gives the total magnetic field produced by the iron rod, which is 12 pi, which is a very large magnetic field, 3 into 10 power 3 is equals to 4 into 10 power minus 3. And also find mu r as well, where mu value, which is equals to mu r value, which is equals to 4 pi into 10 power minus 3 by 4 pi into 10 power minus 7. So mu r, which is equals to 10 power 4, and susceptibility, which is equals to 999. They did not ask us to find the susceptibility. Now let's go to the next question. An iron bar of length 10 centimeter and diameter 2 centimeter is placed in a magnetic field of intensity 1000 ampere per meter. This is H value, with its length parallel to the direction of field, meaning angle between them is 0. Determine the magnetic moment produced in the bar magnet. That is, if permeability of its material is 6.3 into 10 power minus 4 Tesla meter per ampere. Okay, let's read the question again. It's an iron bar. There is an iron bar. Its length is 10 centimeter, diameter is 2 centimeter. If it is placed in a magnetic field of intensity, the magnetic field intensity is 1000 and its length is in the direction of the field, meaning the magnetic field and length vector direction is 0 degrees. Determine the magnetic moment produced in the bar magnet. What is the magnetic moment produced in the bar magnet? If the permeability of its material is 6.3 into 10 power minus 4. And solution, the magnetic the intensity of magnetization, which is equals to chi times h, and we know that I equals magnetic moment of material per unit volume. So when we take m, which is equals to IV, so final formula, m by v, which is equals to chi h, meaning magnetic moment of material, which is equals to chi hv. Now we do not know the value of chi, we do not know the value of v, we do know the value of h. They gave permeability value. We know that permeability, susceptibility and relative permeability are interdependent. So chi, which is chi plus 1, which is equals to mu r value, mu r which is equals to mu m by mu naught. So mu naught times chi plus 1, or basically chi, which is equals to mu m by mu naught minus 1, chi, which is equals to 6.3 into 10 power minus 4 by 4 pi into 10 power minus 7, pi 1s are, pi 2s are, is equals to 1s are, 2s are again, 0.5 into 10 power 3 minus 1. So chi finally, which is equals to 499. Now volume, if we want to find out second unknown value, volume for a cylinder, which is pi r square times L, since pi value 3.14. R they gave diameter as 2 centimeters, so 1 centimeter 10 power minus 2 whole square, and length of the conductor was said to be 10 centimeters, so 10 power minus 1. Finally, volume, which is equals to 3.14 into 10 power minus 5 meter cube. Now substituting all the values, magnetic moment, which is equals to 3.14 into 10 power minus 5 into a magnetic intensity H value, that is 10 power 3 into approximately 500, 5 into 10 power 3. So it will be magnetic moment, which is equals to 5 into 3.14 into 10, that is 31 5s are. Wait a second. So it is approximately equal to 150 ampere meter square. Now I hope I didn't make any mistakes here. Chi value, which is indeed 500. And magnetization, which is also can be written as I into V, where I value, which is equals to chi times H, that is approximately 5 into 10 power 5 plus 5. And this times magnetic moment, which is equals to 5 into 10 power 5 times 3.14 times 10 power minus 4 times 10 power minus 1. This is not 5 into 10 power 3, this is 5 into 10 power 2. So this is not the case, there won't be any extra here. So yes, this is the final answer. This is an approximate value, magnetic moment, which is equals to 15 ampere meter square, and exact value we will get it as 17, a very close value, which is 17.7 ampere meter square. This is the magnetic moment. These are all no wait some of the important question models from magnetism and matter have been solved and completed. Then okay, I will be ending the stream.